object. So far we've been considering just one object, making its free body diagram, then applying Newton's second law using the net force to find the acceleration. Yeah. But if you have more than one object like this is called an Attwoods machine, and you'll be doing experiments using this. It's a very simple machine. You have a frictionless pulley here. You have a rope that connects two objects, object 1 and object 2. We're going to assume that object 2 is more massive than object 1. Therefore, this is going to pull the entire system downwards, yeah, with some acceleration 2, which is going to be the same as this acceleration 1. Since the whole system is connected, it has to move with one acceleration. So if you have two connected objects, there are two ways of studying this system. One is to study the system as a whole, and we'll look at that in the next slide. And the other is to make free body diagrams for each of the two objects, right? And then study them separately, solve those as simultaneous equations, right? To combine them, okay? So let's look at the free body diagrams for each of these. If you consider mass 1, we're going to take a center here for mass 1. What are the forces on it? So it has its weight mg acting downwards, right? And it has a tension in the string upwards, right? It's not resting on any surface, so there's no normal force in this case. So here's the center of mass 1, here's mg downwards, here's the tension in the string upwards. Remember I said the tension has to be the same throughout the rope. It can change direction though. So the pulley helps the direction to change. Here it's upwards. Here also the tension is upwards, yeah? Okay. So these are the only forces on mass m1. We've written them here. The net force is going to be this tension, subtract out this m1g, yeah? That's your net force. And then you can set that equal to m1 times a. That's going to give you Newton's second law for this object, okay? We'll look at that a little bit later on as we do after we finish the whole system. Let's make the free body diagram for the second object. So this is my center of mass for the second object, M2, and it also has the tension in the rope upwards, and it has its weight, M2G, acting downwards. Since we took M2G much bigger than M1, this arrow is drawn much longer than this one. Okay. So let's look at the system as a whole system view. What if M1 and M2 were of equal mass? Then we could have equilibrium, right? Nothing would move. So they only move because one of the masses is much more massive than the other. So its weight becomes greater, and that pulls the system in its direction, yeah? That direction goes down. So it's going to be the difference between M2 and M1 that creates that net force. So difference in weight here. So M2G minus M1G is going to be my net force, which is here, M2 minus M1 times G. I just took out the G in common. This is my net force. It must be equal to mass times acceleration for the entire system. So what's the mass for the entire system? Both these masses need to move. So the total mass is M1 plus M2. Remember, we're going to say the pulley is massless, okay? So it moves without any force required, which obviously is not really the case, but it's a good approximation. If you have a very frictionless pulley and massless pulley. So this is my net mass for the system, M1 plus M2, times the acceleration, which is the same. So A equals A1, also equals A2, okay? If I solve for this acceleration, I get M2 minus M1 G in the numerator, whole divided by M1 plus M2. So this effectively, this numerator is my F net. This is my total mass, right? So I can write here actually, let me just write that to make it more clear, that A equals F net divided by total mass of the system, yeah? Okay. So we have a formula for the net acceleration. Let's look at the system now as two separate objects and then solve those two equations simultaneously. So if we look at the first object, M1, the forces on it were the tension upwards and M1G downwards. So F net here is just T minus M1G. This is my F net. And M into A is just this mass. Only one mass you need to consider now, okay? So M1 times the acceleration. This is my equation 1. I'm going to do something very similar to this, analogous to this, for the other system. Just a second. I just want to clear or dry. Yeah. And let's go to the second system. And here we also have the tension upwards, M2G downwards. So my net force is going to be tension minus M2G. And we're taking that because this is positive and M2G is negative, right? So we just need to do that algebraic sum. That's going to be my F net. And it's going to move this, only this object, M2 times acceleration. So it's my second equation. If you take equation 1 and equation 2 and solve them simultaneously by eliminating T, you will arrive at exactly this which we have seen before. This we saw as the acceleration for the whole system. Okay, you'll be exploring these equations in much greater detail in the lab, but we just wanted to introduce this to you. Okay.